Okay, and now I'm ready to pass the podium to Kyra. And Kyra, please go ahead and then share the screen. I'm going to stop sharing here, and you can go ahead.
Okay, thank you, Ahmed. Let's see. Can you see my presentation now?
Yeah, perfect.
Okay. Thanks for the nice introduction. Super happy to be here presenting about this introduction. So what I'm going to talk about is a bit of an introduction to Luceda as a company, what we do, and how what we do, let's say, goes well together with what Ahmad showed you, the system level simulations, and how can you combine everything together. So for those of you who don't know us, Luceda is a company based in Belgium. We are now 10 years old, born out of the Belgian photonics ecosystem. We are really a photonic design company. So we are a team of photonics experts, and our customers are designers who sell software to design photonic integrated circuits. But we are also an ecosystem company. So we pride ourselves in having many ecosystem partners, among which we can find foundry partners, assembly testing, general ecosystem partners, and of course, software partners, among which Optiwave, with which we just started a new partnership. And what we aim to do as Luceda is to provide a first-time right experience to photonic IC design. And we do that with our products, which are built in Python. So we are based on a code-driven flow, and we bring together all the aspects of PIC design in this one flow so that people can build chips that fit into products and products that work. This is an overview of our platform. Our core product is Luceda IPKISS. This is the platform that centralizes all the design aspects. So you have component and circuit layout, simulation, and ultimately what you do, including validation and verification, it all leads to GDS export, and a GDS export that is correct according to foundry rules. We also have specialized tools that build on top of our core product, and we also have partner integrations such as the OptiSystem Luceda CoSim that Ahmad has introduced. This new integration enables designers to fully simulate photonic integrated circuit-based products in a unified system. So you can leverage Luceda's layout and modeling capabilities of the PIC together with the system-level simulation features of Optiwave. Here you can see a schematic example of what's inside an optical transceiver design. So you would typically have a chip which contains the integrated photonics part, which you can design and simulate with our software. And then you can place it in a system-level environment where you can combine these with, say, the electronic drivers, DSP from Optiwave. So is a screenshot of the tool. Ahmad is going to show this more in detail later. But basically, you have this OptiLUCEDA CoSim component where you can easily embed circuits that you have designed with Luceda. And it can work together with other components that Ahmad showed in his slides already to then run system-level simulations. So the question here is, how do you design the PIC, which is what you would use Luceda for? In Luceda, one flow is able to take into account the layout of the components, circuit, and simulation in one flow. You can do this parametrically, and you can do these according to the constraints imposed by the system and the foundry and the components that you're using. So in many cases, you will start from a schematic capture to, say, ideate on your circuit, think about the high-level parameters you want to use for your circuit or system, and say, think about the high-level specifications. And in a second instance, and you can do this in IPKISS Canvas, which is a schematic capture tool, which is part of Luceda IPKISS. In a second instance, you will start by implementing the components and the circuit you need to let's say, design this circuit in layout. So the first step is component design, which you need unless you're using standard building blocks from Foundry PDKs. You can leverage the standard Python language that we use in Luceda IPKISS. You design components that are parametric in layout and simulation. You can usually fabricate them according to the, let's say, layer stack of the foundry or the PDK that you're using, and run EME simulations or simulations with third-party tools to which you can automatically export the layout you have created in IPKISS. So imagine you have, for example, a directional coupler, and we simulate it in FTTD. Then you can extract the S parameters, import them in IPKISS, and build a model for your components so that you are able to run, let's say, S matrix simulations, circuit simulations at any point in time without having to rerun FDTD every time. Now imagine you do this for a wide range of parameters. So in the case of the directional coupler, you could sweep the straight length of your directional coupler. So you have a parametric cell, you fix with the parametric layout, you fix that one parameter many times, and every time you run simulations. At the end, you can do a fitting of the simulation data with a specific fitting heuristic that is suitable for this component, and you obtain a parametric analytical model. What this means is that in your parametric cell, you can now change this length to the value that you want, and you have a parametric analytical model that will tell you how the component behaves for that specific parameter. And then you can use these smart components in circuits. So here we're implementing the schematic we saw earlier, which is a wavelength demultiplexer. So you have, if you have two wavelengths in inputs, you can split them and the two outputs. And here, basically, what you can implement in a IPKISS cell that synthesizes this layout is a synthesis algorithm that basically takes the behavior you want your system to have and relates that to the design that you need to achieve. You need to achieve that specific behavior. So what does it actually mean? In the case of the multiplexer, you want to control the FSR, you want to control the center wavelength. So these will be the parameters of your cell, and in the back you have Python code, IPKISS code that do all the calculations of the physics to basically implement the right layout with the right length difference between two arms of an MZI, with the right straight length of the directional coupler to obtain this kind of transmission spectrum. And in the next step, you can then build more complex circuits. So here we are cascading MZI, basically the same multiplexer you saw earlier can be used as a cell that is then cascaded in a sort of tray. So if you have 8 input wavelengths in this circuit, they will be split among the 8 outputs. And this will be a type of, let's say, output simulation that you achieve by simulating such a circuit in IPKISS, where you keep a tight link between the layout and the simulation. So if the layout changes, you will see that in your simulation as well. And all these circuit design is backed up by foundry PDKs, so you can design custom building blocks and use them together with foundry building blocks. And very importantly, you also combine that with, let's say, requirements from assembly and testing in what we call assembly design kits or test design kits. And of course, the same flow that I showed you so far, so we saw that for the multiplexer, you can use it also for active components tailored for the application that you need to design for. Yeah, for instance, here you see an IQ modulator designed with your software for datacom applications, or an optical phased array for LiDAR applications. And you see these circuits being part of a packaging frame provided by PICs, which is automatically including your design through code. So you can follow this parametric framework where you can interchange and combine components you design with building blocks from PDKs. And then the behavior of these circuits is simulated according to the models built at component level. And then you send signals in, read signals out, and see how the circuit as a whole behaves as a combination of all these subcomponents. And it is really where the integration comes in, because you can load these circuits inside OptiSystem and then manage your system simulation inside OptiSystem by deciding, basically defining all your inputs and defining all your outputs, how you want to read your signal, what kind of information you want to get out of your system. You define the figure of merits that you want. And again, you can combine the Luceda component with all the other components from OptiSystem. As a final step, we have verification and tape-out preparation. So it's something you can do in IPKISS is like in the end, what you're going to send to a foundry for fabrication is the GDS file of your layout that you have simulated and validated for simulation, but it also has to be correct in layout. So you want to check that the optical connectivity, it doesn't have mistakes and is implemented correctly, and that you don't have electrical shorts, that the waveguide lengths are implemented as intended. You can extract the netlist automatically to verify it, run post layout simulations, also in OptiSystem, of course. Many of our customers also use 3D Expert to verify the circuit or to just import the 3D model of a circuit in whichever tool they need to import it into, whether it's a simulator or a 3D visualization tool. And also very importantly, you have to prepare your designs for tape-out. So making sure that your design is accepted by the foundry, that you get rid of small, let's say, design issues that would not be accepted by the foundry. They would be raised by DRC. And they're talking about DRC. We're talking about design rule checking. So something that you can also do with Luceda is to create your layout using IPKISS and then run DRC using a single line of code. In this case, that's implemented with the link for Checkmate DRC, which is the recent tool developed by Spark Photonics. It allows you to run DRC checks on your layouts and then open them in KLayout. So circling back to conclude to the integration with Optiwave, the key benefits are that you can combine the layout and modeling capabilities of Luceda. So what I showed you now, I gave you an introduction to, together with Optiwave system simulation. And this doesn't require any manual translation, as Ahmed will show you in a bit. So you can embed photonic integrated circuits that made with IPKISS inside OptiSystem without having to manually redefine ports or manually extract the netlist. And this gives you like a complete electro-optical system digital twin. This can be done for many applications. So I showed you before a schematic of an optical transceiver, but it's just an example. Actually, we are very interested to see what you do with this. You could use this for quantum key distribution, LiDAR sensing, think about designing AWGs, array waveguide gratings in Luceda, and then simulate them in OptiSystem. So there are no real limitations on applications, and we are curious to see what you're going to do with this. And I guess I'm going to stop sharing my screen now and get back to Ahmed.
Perfect. Thanks, Kara. I think that's very, very good and very interesting for this kind of integration to allow users to characterize photonic integrated circuits designed by Luceda and into OptiSystem. So what I'm going to do here, it's show an example quickly about ring resonator, which is designed by IPKISS and then used for demultiplexing for DWDM channels. And it's characterized in a layout in OptiSystem. So the example, what we did here in the example, I'm going to show you in a minute in real life, but it's in the component here, which is the OptiLUCEDA component here, co-simulation. We did first the characterization of the frequency response of the components. So what you can do, you can send an impulse here into the component and then characterize the output at every port of the component. And in the second part of the example, as you can see here, you can take a look at the response of the channels at the output port. And the other part of the example is we modulate different DWDM channels. As you can see, 4 of them here, multiplex them, and then transmit them through the big ring resonator demultiplexer, and then basically demultiplex each channel. And you can look at the output of any channels here and characterize the bit error rate, the Q factor, and how is it the device. Now, you can do a live different sweeps of parameters in the PIC design, and then every time you can take a look about the output results. So because OptiSystem allow you to sweep the parameters, you can do the sweeping and then look at the results. So let me go into the example here, which is going to another virtual machine here I have. And in this example, you can see we have pseudo-random user-defined, this component called user-defined bit sequence generator. We send only one bit here, eight of them, and one of them is 1 and the other one is 0. And then you send it into these impulses. Now, in the main layout, you can set up the bit rate, you can set up the sequence length. Here we have 8. You can have the number of samples per bit, and then baud rate. This is for other application and so on. But once you set it up, you go to the Luceda component, and the Luceda component is very simple kind of structure for the component. You have you can select the domain. It is a frequency domain or time domain of the calculation. You can you can either specify the path for IPKISS locations, or you can automatically detect that. In here, we can detect it automatically. Also, you can load the PIC file. So you can click on this icon here and then load the file from its location, as you can see here. And then once you load the file, what you can do the run button here. And this, once you do the run button, the component will be populated by the ports, input ports and output ports, depends on the design of the PIC. And then you can look at the PIC port information, as you can see here. So describing all this PIC information. If you enable this one, and you can take a look at all these ports and description of them. And then here, if you want to delete the file, you can click here, delete. So you can delete the file and then load another file if you wanted to do that. Once you do that, you can do the calculation. Once you do the calculation, I did the calculation ahead of time, and then you can take a look at results at every port of this demultiplexer. And this is the drop channel, as you can see here, the pass-through. And this is each drop channel. Now, the other layout, because OptiSystem allow you to have as many layout as you want, you can duplicate the layout as is, or you can create your empty layout. But in this layout here, this is the example where we use the system characterization of the PIC demultiplexer. We load again the PIC file, same scenario, and then create the ports. You have input ports and 5 output ports. And you can set up random bit sequence and lasers, the type of modulation which you require to analyze this device with. You can get benefits from using the example library, which allows you to build on these systems. And then here at the device, as you can see, we have placed the spectrum analyzer, optical spectrum analyzer. As you can see, this is the new feature added about the calculation of the resolution bandwidth at specific wavelength. And you can also have the pen detector. If it depends on the application, you can have pen or APD or SPD and so on. And you can have 3R regenerator, or you can build your own system by connecting the reference pulses and so on. So there is different options to have. And then this is the eye diagram where you can analyze the Q factor, the bit error rate, and so on. You can, any of these components, by the way, if you right click on the component, you can have component results. So you can have the available results in the component. You can have, as I showed you before, the component view, which you can take a look at some results here. If there is some plots, it will appear here. You can have 2D plots, you have 3D plots, you have reports. We have lots of webinars which explains more details about the software. But as you can see here, with the integration of this component PIC device, you can analyze, you can do sweeping, you can do a lot of parameters to do a simulation ahead of building the device and investigate the device thoroughly. We will have another webinar actually on let me just get out here. We're going to have a more detailed webinar with Luceda, talk about the process thoroughly, and in maybe a month or 2 months time frame. Okay, so this is kind of the results. Now, just to summarize here, we have this collaboration with Luceda to characterize photonic integrated circuits within a system. And you can look at IPKISS through the website of Luceda or this QR code. And also you can download OptiSystem software or other package of software through the website, and you can download 30 days free trials. I think with this, I conclude the webinar. Thank you very much for listening, and now we are open for questions.